Good morning, everyone. And I'm here to present my thesis on deep learning for predicting and classifying the dynamical behavior of piecewise smooth maps. And in the study of complex system for predicting and classifying the dynamical behavior of the system, it is important to understand how the state of the system changes with time. Dynamical systems are mathematical models that describe how the state of the system evolves over time. For a wide range of applications, ranging from predicting weather patterns, controlling complex machineries, and modeling biological systems, understanding the behavior of the dynamical system is important. For example, in biological systems, dynamical models explain population dynamics, the spread of diseases, and the functioning of cellular processes. Piecewise smooth maps are mathematical models which show both continuous and discontinuous behavior. At the boundaries between the region, the map shows discontinuities, and the map also shows continuous behavior within each region. The combination of these regions and discontinuities can lead to complex dynamics which include phenomena like bifurcation, chaos, etc. The piecewise smooth maps show a wide range of dynamical behavior such as regular, chaotic, and hyperchaotic behavior. Understanding the behavior are important for various applications like control system, cryptocurrencies, etc. Border collision bifurcation is a distinct type of bifurcation occurring in piecewise smooth maps when a fixed point or periodic point collide with the boundary region. Most of the bifurcations seen in power converters are border collision bifurcation. Unlike other bifurcations like saddle node bifurcation, transcritical bifurcation, pitchfork bifurcation, etc., border collision bifurcation can lead to sudden changes. For instance, a stable fixed point can suddenly become unstable and bifurcate to a chaotic attractor. This feature is not seen in smooth maps. Border collision bifurcation are important to understand the evolution of piecewise smooth map system, especially in the context of stability analysis and control systems. Predicting border collision bifurcation is important for understanding the dynamical behavior of the system that exhibit piecewise smooth dynamics. Here, a novel approach is introduced, that is predicting the border collision bifurcation of the piecewise smooth maps using machine learning. For that, two simplest piecewise smooth maps are considered. 1D normal form map defined by the equation xn plus 1 is equal to axn plus mu for x less than 0 and bxn plus mu plus L for x greater than 0. And 1D tent map is defined by xi plus 1 is equal to mu xi for x less than 0.5 and mu into 1 minus xi for x greater than 0.5. This is the one parameter border collision bifurcation diagram of 1D normal form map, and this is the border collision bifurcation diagram of 1D tent map, where we can see that in one-dimensional 1D normal form map, mu changes from minus 0.1 to 0.2, and for 1D tent map, mu changes from minus 2 to 2. Because of the presence of periodic behavior, it is necessary to find the period of the orbit. Detecting the periodic behavior includes simulating the system's behavior and then observing the trajectory. If the trajectory returns close to its starting point after a certain number of iterations, then it shows periodic behavior. Now, to determine period, we will count the number of iterations required to complete one cycle. In this way, we can determine the period of the orbit for a particular value of parameter. Next, we want to know at which value of mu border collision bifurcation occur. For convenience, we start with period 1 and apply the condition, that is at which value of the parameter mu x collides with the boundary. This shows a one parameter diagram of period versus mu of normal form. And we can see that when parameter mu changes from minus 0.1 to 0, the period is fixed, that is 1. When the parameter mu is 0, then the period increases suddenly and reaches to 9. This is because of the presence of border collision bifurcation. And also when the parameter mu is at 0.1, the period decreases suddenly and goes to period 1. This is also because of the presence of border collision bifurcation. And this figure is the 1D one parameter period versus mu of 1D tent map. It shows that as parameter mu varies from minus 1 to 1, and the period increases gradually for each step, and this is a sudden increase in the period at certain value of parameter mu because of the presence of border collision bifurcation. And finally, the parameter value mu is predicted where the border collision bifurcation occurs. For 1D normal form map, the values of parameter are mu is equal to 1.38 etc. is raised to minus 17 and mu equal to 0.1100 etc. 3. For 1D tent map, they are mu equal to minus 0.98 and mu equal to 0.988. For higher order, it is difficult to predict border collision bifurcation manually. So here we are introducing a novel method predicting border collision bifurcation using machine learning techniques. For that, 5 machine learning models are used: decision tree classifier, logistic regression, K nearest neighbor, random forest, and support vector mesh. The data is generated by simulating the equation for varying values of parameter. It observes how the system states evolves for each parameter mu, identifying periodic orbits and recording details such as mu, final state, and period. The data is split into training 80% and testing 20% set. The data is trained with 5 machine learning models and accuracies are calculated. For 1D normal form map, from the accuracies given, we can say that random forest is more accurate than other models and best for predicting border collision bifurcation in 1D normal form map. And for 1D tent map, from the given accuracies, we can say that decision tree classifier is more accurate than other models. Also, we used heat map of period versus predicted values. Here from the heat map of 1D normal form and 1D tent map, we can say that random forest is best for predicting higher periods of the orbit as the intensity is high, which is denoted by dark green color. And border collision bifurcation lead to sudden changes like fixed point after colliding with the boundary can bifurcate to a chaotic attractor. So there is a need to predict, there is a need to classify the regular and chaotic behavior of piecewise smooth maps. Here we considered 2 piecewise smooth maps, 1D tent map and 2D lossy map for classifying the regular and chaotic dynamical behavior. For 1D tent map, data is generated by simulating the equation for different values of mu. The Leopold exponent is computed for 1000 randomly selected values of parameter in the range of minus 1.5 to 1.5. If Leopold exponent, that is lambda, less than 0, then it is regular, and if lambda greater than 0, then it is chaotic. Here we used Copework diagrams as data for training and testing. Then the 2D lossy map is defined by the equation xn plus 1 equal to 1 minus a mod xn plus yn and 1 yn plus 1 equal to bxn. Here also, data is generated by simulating the system equation for a parameter a from minus 0.1 to 1.7, while keeping the parameter b equal to 0.5 as a constant value. For each value of parameter, Leopold exponent is calculated. Here we used phase portraits as data for training and testing. These are the cobweb diagram and phase portrait of 1D tent map and 2D lossy map. Here we used deep learning models for classifying regular and chaotic dynamical behavior. Deep learning models are convolutional neural network, ResNet 50 and convolutional LSTM. And the data set is splitted into 70% for training and 30% for testing. All the three models are trained and accuracy is calculated. From the accuracies given, we can see that for 1D tent map and 2D lossy map, CNN is best for classifying regular and chaotic dynamical behavior as it shows 100% accuracy. Additionally, we calculated the accuracy in the test set of regular and chaotic samples. For tent map and lossy map, regular three models show 100% accuracy in predicting the regular behavior, and CNN show more accuracy for chaotic behavior. And we already discussed about 1D and 2D piecewise smoothness, and also chaotic and regular. But hyperchaotic behavior can also occur in border collision bifurcation. So here we are considering three maps which show hyperchaotic behavior. They are 2D membrane map, 3D hyperchaotic map, and 3D piecewise smooth maps. The data is generated by simulating the equation for a range of parameter values, and Leopold exponent are calculated. For 2D membrane map, the parameter k is varied from 1.6 to 1.8. For 3D hyperchaotic map, the parameter B2 is varied from 0.512 to 1.1, and 3D piecewise smooth map, delta R, the parameter delta R is varied from minus 1.05 to minus 0.8, and the other parameters as follows. The figure shows a border collision bifurcation diagram and corresponding Leopold exponent spectrum of three maps. Here, if lambda 1, lambda 2, lambda 3, that's three Leopold exponents less than 0, then we can say that it's a regular behavior. Either lambda 1 or lambda 2 or lambda 3 greater than 0, then chaotic. More than 2 Leopold exponent positive, then hyperchaotic. Here also we use three deep learning models for classifying chaotic and hyperchaotic behavior. They are feed-forward neural network, long short-term memory, recurrent neural network. The data is splitted into training 80% and testing 20%, and the accuracies are calculated. From these given accuracies, we can see that LSTM is best for predicting LSTM is best for classifying chaotic and hyperchaotic behavior. This is a figure shows the comparison of predicted behavior with Leopold exponent spectrum. The blue shows FNN, red shows LSTM, and green shows RNN. And the light colors shows that it represents the regular behavior. Dark colors represents chaotic and black hyperchaotic. From this figure, we can see that apart from FNN and RNN, LSTM predicted chaotic behaviors. Moving to the next section, to know more about the dynamical behavior of piecewise movement, we use two parameter charts. Here we are reconstructing the two parameter charts with the help of deep learning models. Two parameter charts are tools used in the field of nonlinear dynamics and the chaos theory to study the stability and behavior of the dynamical systems. They are used to visualize how the system's behavior changes when parameter varies. Here we consider 2D border collision bifurcation normal format. And the data is generated by simulating the equation for varying parameters, that is 2L from -1 to 3 and 2R from -0.2 to 1, and the other parameters as follows. For regular, and this is for a 1,000 cross 1,000 grid points, and Leopold exponents are calculated and labeled as, for regular it's labeled as 0 and for chaotic as 1. Using this, a biparametric plane is plotted. The figure shows the biparametric plane where A represents the biparametric plane where each period is differentiated with different colors. And the second, and the B figure shows that blue represents the regular and red as chaotic. And here we use two deep learning models, that is RNN and LSTM. A subset of the biparametric plane is taken for training the model, that is tau L from 0 to 2 and tau R from 0.6 to 1. After training, the labels are predicted for the range of parameter tau L from -1 to 3 and tau R from -0.2 to 1 and plotted as follows. These are the predicted two parametric plot charts where A is the original image, that is the image we got from actual data, and B is the predicted values and plotted where we use the RNN, and C is the plot we get when we use LSTM. And these are the accuracies we obtained. From this, we can say that LSTM is more accurate than RNN and best for reconstructing the two parameter chart. And the conclusion, for predicting border collision bifurcation of 1D normal format, random forests show more accuracy, and for 1D tent map, decision tree classifier shows more accuracy. And for the classification of chaotic and regular behavior, CNN is suitable. And when it comes to the classification of chaotic and hyperchaotic, LSTM shows more accurate. Finally, for reconstructing the two parametric charts, LSTM is more precise than RNN. And the future scopes include, we can use deep learning for predicting higher order periods, and also we can use deep learning in cobweb symbiosis, as nowadays cobweb symbiosis is very hard and it's done manually. When we can apply deep learning, it can be more effective. Thanks.